Okay, let's take a look at a special type of acceleration or a special case, and that's constant acceleration. Constant being the key word here. I'm going to denote constant acceleration with a subscript of c. And all a constant acceleration means is that that acceleration is literally just a number with the units meters per second squared attached. So it's not a function of time. It's not a function of anything. It is constant. And if we look at, we saw some inflection in a position versus time graph before. A constant acceleration will produce a parabolic curve. So this is position versus time. And we can go to velocity versus time, where if that is a constant acceleration produces a straight slope or a straight line on the velocity versus time graph. That slope is equal to the constant acceleration. Okay, and then if we wanted to look at the acceleration versus time graph, if it's constant the whole time, we're just gonna be holding it at some value. So the slope will be 0 at a constant acceleration on a acceleration versus time graph. Okay, wanted to put that out there, and then I'm going to briefly go over section 2.4. But I'm going to teach you how to get these equations from 2.5 using calculus. This is calculus-based physics. So go ahead and please read through 2.4. There's some good stuff in there. But they find all of these definitions right here. And this is from table 2.1 in your book. And you've seen at least these ones before. Those top three. You just might not know where they came from. They derived them using average acceleration and average velocity. I'll do one real quick. They say the average acceleration by definition, right? It's v final minus v naught over delta t. If it starts at t is equal to 0, we can end up arranging this thing to look like v naught plus acceleration times time. There's one of our equations right there. But this is not the method I would go about deriving the equation. And that's because our accelerations are not going to be constant always. If you do it in the method I'm about to show you using calculus and integrating, then you can put in your function of velocity, and it doesn't have to be constant, and we can get our new equations of motion. Just all depends what we're given. There's every different case you can think of. But you can get these two equations from those. What I'm going to do for you is show you how to get those top three equations. The bottom two are just by eliminating a variable using algebra. So let's get those top three. This one right here, this one right here, and this one right here. And let's use calculus to do it. Okay, so the reason I like this method is because all you have to do is remember a definition. And it works for non-constant accelerations too. So I'm going to denote constant acceleration as a sub c. And let's start out with the definition of acceleration. That is equal to dv dt. This is a definition. You need to remember this. And if you're taking dynamics ME 242, I really don't like having to teach this again. I have to go through a lot of basic physics in there, so that's one of my jobs, is to hopefully teach you the skills to move on to dynamics without having to refresh too much, because we'll definitely be doing this in dynamics class. Okay, all we have to do is separate our variables and we get dv is equal to the constant acceleration times dt. Now let's just integrate both sides. We can move the second integrand just outside the dt because this is just a number, it's a constant value. And what do we get? Let's integrate this from v naught to v final. Let's integrate this from t naught to t final. Well, I get This one will give me v evaluated from v naught to v final. And this one will give me the constant acceleration times t. And we have to evaluate t from t naught to t final. This is going to give us velocity final minus the initial velocity is equal to the acceleration times t final minus t naught. Alright, we got our first equation. We can throw this on the other side and say v final is equal to v naught plus that acceleration. And we can just throw time in there, whatever the time interval is of interval. So there we go. We have one equation without using any average definitions or average velocity definitions, average acceleration definitions. We started with the calculus derivative definition. Okay, let's keep going. What other definition do we have so far? We have that velocity is equal to dx dt, the rate of change of position with respect to time. So this is another, you can get these equations by just remembering these definitions. If I take dt, separate the variables, I get v dt is equal to dx. I'm going to actually rewrite that. Dx is equal to v dt. And what we need to do is take our answer for v and put it right there. So I get v naught plus our constant acceleration times time. And that needs to be integrated with respect to t. So let's integrate the left-hand side from x naught to x final, and the right-hand side from t naught to t final. Well, that's going to give us an x, and when we evaluate it, we get x final minus x naught. And when we integrate v naught, that will just give us v naught times time, and when we integrate the acceleration times time, this term right here, we will get a 1/2 at squared. This whole thing, we can say it's evaluated from 0 to t final, and it'll reduce down like this. Don't just remember, it doesn't always start at t is equal to 0, right? And then we throw this term on the other side. We get x final is equal to x initial plus the initial velocity times time plus 1/2 constant acceleration times time squared. Ta-da! There's your second kinematic equation. Alright, we can get one more by eliminating dt. So let me show you what that means. So I'll write it down. Eliminate dt. So we have acceleration is dv dt. That's a definition, right? We also have a definition of velocity is equal to dx dt, the time derivative of position with respect to time. Let's solve these things for t and set them equal to each other. That would give me dt is equal to dv over a for this one. And on this definition right here, get dt is equal to dx over v. Alright, let's set those equal to each other then, because they're both equal to dt. I can say dv over a is equal to dx over v. Alright, let's go ahead and make it a little cleaner, separate the variables. Let's get this v on the same side with this v. So I get v dv is equal to a dx. So you can just go ahead and remember this. And let's say you had acceleration as a function of x. That's something we'll have well, put it in there and we can integrate it and get our equations of motion. But in this case, we're going to integrate this from v naught to v final. And we're going to, since this is constant, we can just integrate the dx from x naught to x final. So we get a v squared over 2 when I integrate the left-hand side. And we still need to evaluate it from v final to v naught. On the right-hand side, when I integrate it, we still have a constant acceleration. And that needs to, once we integrate dx, that gives us x, and then we can evaluate it to be x final minus x naught. The left-hand side, let's go ahead and throw this 2 over here first. And that's going to give me, after I evaluate it, v final squared minus v naught squared is equal to 2 times the constant acceleration times x final minus x naught. And when I throw this over, you will recognize the equation as our time independent equation. Notice time is not in there anywhere. And the most important thing about these is these only work for constant acceleration. So projectile motion is a great example of this. When we shoot something out of a cannon, it has a y component we'll learn and an x component, some vx and some vy. We have to treat each component differently, and we're going to use these kinematic equations for each. Unless there's drag, though, I'll show you that the velocity in the x direction remains the same. So at any given point, the component in the x direction has the same magnitude. But if it's going up to the top here and turning back around and coming down, that means the velocity in the x direction eventually gets smaller, goes to 0, and then ends up coming down in the other direction. Okay, I'll go over this plenty over projectile motion and motion in 2 dimensions. The other 2 equations in your book, these ones right here, can be made from eliminating variables. I really recommend just remembering those 3. When we get to motion in 2 dimensions, you don't have to remember for the x and the y. We just look at, hey, is there an acceleration in the x direction? If there's not, no, there's the v in the x direction final is equal to the velocity in the x direction initial. And I'll show you all that stuff too. I'm just giving you some examples. Just seeing if I see anything in particular in my notes. Really though, you should definitely read section 2-4. That's because it's going to introduce the constant acceleration. And then 2.5 is going to do what I just did. It's going to derive them with calculus. So you can look over it too, but I pretty much just did that for you. Alright, I think that's it for now.